Next speaker here today is John Sloan with AECOM to talk about the Swift Island Historic Arch Bridge Preservation Project. John?
Thank you, Tim. Thank you, everyone. So the Swift Island Historic Arch Bridge Preservation Project is a bridge here in the southern Piedmont of North Carolina, not too far from Charlotte. It's over the PD River. Before we actually talk about the preservation project, it's important to talk a little bit about the history of the bridge, because there's a very fascinating story, some fascinating stories that we can tell about the project. So early days over the river, there was a ferry. Then in 1922, there was a arch bridge that was constructed. Then in 1927, the arch bridge that we actually rehabilitated was constructed. And in 1979, there was another bridge that was constructed over the area, over the lake. So 1922, the original bridge was constructed, but then just a few years later, they decided to build a dam downstream to create the lake. So there's some footage of the actual construction of the dam. You know, what are you going to do if you've got a brand new bridge that's going to be destroyed by the dam? Well, first you have to build a new one, but then from there, you go do some load tests, right, on the older bridge. So there were some load tests that were conducted on the 1922 bridge, the original bridge. They put these massive water tanks out onto the bridge, 164 tons per tank. That's an immense load. They took measurements, as you can see in some of the photos there. Very fascinating footage here. And this is all available on YouTube. So you can go out and Google search for it, America's Great Bridge Test. Well, then what do you do after you do your load testing? Well, you hand the bridge over to the military so that they can engage in some exercises, some target practice. You know, that's a howitzer and airplanes and bombs and so on. Pretty impressive stuff. Watch this one. There you go. So they were actually conducting a very scientific evaluation, right? So they shelled it with smaller shells first, then another larger shell, 155 millimeter shell. Then they shelled it with 240 millimeter shells. So, you know, if you want to make the bridge impassable, you know, the lesson is make sure you use a 240 millimeter shell. So in 2015, 2016 timeframe, NCDOT was planning for the widening of NC 24 and 27 in the area from Albemarle out to Lake Tillery, this bridge. And they were looking at different alternatives. One would be to construct a new bridge to the south that's shown there in the red and preserve both of the original bridges. The arch bridge would become a bike and ped facility. Another alternative was to tear down the arch bridge and replace it with a conventional bridge. Neither of these alternatives was ideal, and in fact, alternative one became infeasible due to some politicking from the legislature. So NCDOT found out about a bridge project that AECOM had done in Knoxville, Tennessee. This is the Henley Street Bridge in downtown Knoxville, where we removed the superstructure and then reconstructed a new, wider superstructure. So that NCDOT was very interested in making sure that we could look at widening the bridge. So we conducted a feasibility study to evaluate whether or not the bridge we could do this concept with the Lake Tillery Bridge and actually widen the structure and take the additional load. So this is a basic scope of work of what we did. We did some 2D analysis, inspections, material evaluations, planning, and final summary document. This is a basic rundown of the original structure and some terminology. You have the open spandrel concept, so those are the spandrel vents, the crown of the arch rib, the spring line, and then for the superstructure we had a 3-girder RCDG system. These were the original plans that we had to work with. Very challenging to read, but we could work through it. We could get out your magnifying glass and put the pieces together on it. There are a lot of expansion joints. There were a lot of expansion joints in the original bridge. 2 expansion joints at each pier, and then at the 1/3 points of each arch span. So there was, as we went through the inspection, what we found was there were a lot of issues with the concrete at the piers. You can see just how badly deteriorated that concrete is. Very high chloride content in the pier concrete up by the expansion joints. Further down, variety of items that you see there, cracks, delaminations, and spalls, various levels of degradation. Even further down on the arch piers at the waterline, there's some scaling. And then, you see the acoustic image there. Below water, everything looked really good. That scaling is not a big deal. The main arch piers that needed to remain in place to preserve the arches were in very good condition. The arch ribs themselves were in good condition. This is a really neat photo. I don't know if you can see the grain of the formwork. This is outside, exterior, okay, to the arch rib face, and there's formwork grain that's visible. That grain is 90 years old and hasn't been worn down. So that's a very good indicator of good concrete. There were some cracks underneath of the expansion joints, again at spandrel vents 4 and 8, indicating some chlorides. We did find some chlorides in these areas, but nothing too severe or too bad. SEBA did a service life analysis for us, did some cores and so on. So this is kind of a summary of what SEBA did for the service life analysis and the material testing. Strength was very good. Minimal loss of alkalinity. Petrographic evaluation was very, very good. And again, about the only downside is the high chloride content near the pier expansion joints. We had the visualization shown here that we showed to the State Historic Preservation Office as we talked through this concept with them. And they were actually very excited about it. So these are kind of the results of the planning aspects of it. This was the least environmentally damaging, practicable alternative in accordance with NEPA. De minimis impact, no adverse effects. And good news too, right? We're saving money with this alternative compared with constructing a brand new 3rd structure. On the engineering side, it was very important to NCDOT that this project would last for another 75 years as if it were a new bridge. The department didn't want to do this for 20 or 25 years. So the service life analysis was able to confirm the anticipated life was going to be another 75 years, which is good. So that brings us to final design. So here's a image of the typical section. We went from a 3-girder system to a 4-girder system. We had originally, again, it was 20 feet wide between the rails. This is all the way out to 36 feet wide, so we've got 2 lanes and nice shoulders, 9-foot girder spacing, and then we utilized the precast fascia panels to replicate the facade. I'll show some images of that later on, some before and after images as well. In order to establish geometric control early on in the design process, we got a laser scan, and that basically established not only the horizontal geometry, but also the vertical geometry for us. We made sure that the spandrel vents were in the right place, where we were expecting them, so that we didn't have to adjust girder lengths and so on. We also looked at, again, the vertical because you've got deflections that you have to deal with, and you have to make sure you maintain geometric control as you remove the superstructure and then replace a new, heavier superstructure. So we were able to evaluate all of that, and having the laser survey was a huge help for that. Again, we've got 4 arch spans, and I'm going to talk about some of the behavior of the modeling and the analysis. 4 arch spans, 210 feet per arch span, 33 foot 6 inch rise. That's actually not super high. The piers are tall. They're very tall. They're 50 feet high in water there that you don't see under the water. And then the expansion joints that are there at spandrel bents 4 and 8 have a really significant impact on the behavior of the arch rib below. So if you imagine the discontinuity, you think of the discontinuity there in the superstructure, that creates demands in the arch rib right below it. So there are high bending moments, positive bending moments in the arch rib right below that expansion joint. The new proposed superstructure, we looked at eliminating those expansion joints. We made the superstructure significantly stiffer to relieve loading off of the arch ribs. And we also were able to utilize the additional dead load to our advantage, because you've got a compression member that's lightly reinforced. And so if you've got a concentrically applied load, that's actually a good thing. It helps you resist bending moments. So this shows our model. We started our staged construction model basically at the top image there, just the arch rib. Then you construct the spandrel bents. I should have backed up here for the demo, or I take a pause here and talk about the actual demo. This is photos that PCL gave to us. They were the contractor on the project. The way that they demolished the superstructure is they basically just saw cut all the way through the superstructure at the spandrel bent and removed a whole span between spandrel bents one at a time. And they had to do that in a very precise manner to make sure that the arch ribs did not get overloaded, and you didn't overload one span versus another span, and so on. So you had to be very delicate with that process. Then in terms of the reconstruction of the new superstructure, these are the new box beams between the spandrel bents. And you look at the upper left, it's on the barge, it's about to be set. Then in the upper middle, it's got reinforcing that extends out of the box beam so that then it could be tied together over the spandrel bent, which you see in the upper right. So these are fully continuous. Once you pour the splice, we just call these the concrete splices at the spandrel bents, which the poured concrete you can see in the bottom left. So once that is poured, it's a fully continuous moment connection. So then you get to the bottom right photo, you've got a fully continuous box beam from one pier all the way to the other pier. And when you combine that with a tall bearing that's relatively soft, when you apply the deck load, okay, the deck panels, precast deck panels, and then the concrete deck, those box beams are carrying load, and they're relieving load off of the arch ribs. So this is how it looks in the model. Again, the upper image, you've just got the box girders set in place. Then you're pouring the deck in the lower image, and those box beams are sharing the load in combination with the arch ribs. So it's a complete structural system, not just simple spans in between the spandrel bents. You've got a full system that's acting and behaving together, and it enhances redundancy significantly, and it's a significant benefit to the existing original portions of the structure. Here's an actual photo from construction of the deck. The PCL actually utilized the parallel bridge to pour the deck at night. This image, sorry, it's a little bit difficult to see, but these are interactions of the arch rib. So on the right, you've got the positive moment region where we had the expansion joint at spandrel bents 4 and 8. The orange dot is the old system, and the green dot is the new system. So by eliminating that expansion joint, we've significantly improved the behavior in the arch rib. Similar at the spring line, we added the axial load and we're able to get the demands farther away from the interaction diagram curve. So we've improved the behavior with the additional load and the new system. We were able to eliminate 15 expansion joints. So that's going to help a lot with the preservation of the new structure, in addition to the behavioral benefits that you gain from it. Again, box girder continuity, we completely demolished and reconstructed all the approaches as well. The one in the upper right, I'll highlight. If you're working on an arch rib, again, a compression member, if you use a DC factor of 1.25, you're probably going to be non-conservative. You've got to use 0.9 because, again, if you're designing well, the dead load is helping you. The additional dead loads are a benefit for that lightly reinforced compression member. So we used DC factor of 0.9, and then another good thing in the analysis too is all the original reinforced concrete was uncracked. So this is some photos of before and after of the original bridge on the left and the new bridge on the right. There's the barrier rail. We had to have a solid rail for safety reasons, but we were able to mimic the original rail. And you got the arch pier, spandrel vents, the pedestal. So that pedestal on the right is the original pedestal, and then going up from the column, that's all new construction. There's the haunch of the spandrel vent and the fascia. Again, the original fascia was cast integrally with the girder, the exterior girder. Our new fascia was a precast panel. And the typical section, again, 20 feet on the left, 36 feet on the right. And the profile. We also were able to rehabilitate the parallel bridge, Bridge 50, which is a steel girder system with hammerhead piers. So this photo shows the bearing replacement. There's hydraulic lines going down to the barge, from the barge all the way up to the jacks. The contractor had a nifty idea here to install a big strong back diaphragm. They removed the K-frame diaphragm and put this big strong back in that they were able to utilize to jack up the bridge and then pull out the bearing and put the new bearing in. There was alkali silica reactivity in the hammerhead piers. So the overhang is shown there. It's got some epoxy repair that we think dates maybe to the late 1980s or early 90s. We don't actually have a record of that, but I think we know it's earlier than 96, something like that. We had cracks in the water line. Those cracks are up to about a ½ an inch wide right at the water line. We did some 3D imaging with our drone capabilities, created a model so we could quantify the cracks and evaluate the structure with the model. These are just a few notes about ASR. Again, it's a chemical reaction between the aggregate and the cement. So, of course, that's bad news for concrete. It creates a gel as a byproduct of the chemical reaction, which fills all the voids and expands and then, again, causes cracking. So this might be the most fascinating slide on the whole thing. This is really a neat image here. Where you see these thin little veins of ASR activity. This is actually very unusual. The petrographer was fascinated by this. Normally the whole piece of aggregate is reacting, right? But in this case, on this bridge, the ASR activity was occurring just in these thin little veins. Some of the aggregate particles, you have the red dots where the cracks extend from the aggregate into the surrounding cement paste. Then you've got green dots where the cracks are fully contained within the aggregate particle, and the yellow dots where there's no cracking at all. One good thing that we had going for us was a high degree of confinement in the shear reinforcement. So if you've got all this confinement, this reinforcing steel, this is a cross-section of the column steel. Note how there's reinforcing all throughout the center of the column, not just around the edges. So this confines the, as the concrete expands, it provides confinement for all of the material there and helps hold it together and preserve the concrete strength, the compressive strength. So that was another good thing that we had going for us. So here's just a brief summary. Low to moderate ASR damage in the structure. Again, with ASR, water is needed for the chemical reaction, so preventing access to water in the future helps preserve the structure. So we basically did an epoxy jacket at the pier columns, epoxy coating at the pier caps, silane coatings at the column, and then in addition to the conventional rehabilitation items, PPC overlay, painting the beam ends, and the bearing replacements. For construction, NCDOT decided that they wanted to utilize the design-build procurement process for this, and that was mainly because they wanted to vet the contractors with a technical proposal. So the plans that were constructed were the plans that AECOM had developed and we had developed. But going through the design-build process, the contractors had to submit a technical proposal, which was then evaluated by the department and given a technical score. So the department appreciated this part of the process on such a challenging construction project. And AECOM was able to serve as NCDOT's engineer throughout construction of the project. And that's it. Are there questions? I don't know.
So were you surprised that there wasn't a carbonation issue, and was that attributed to just good original quality? I'm surprised, 90 years old, you didn't have an issue there.
I was not super surprised because we were able to get out and see the structure visually before we got any of the material testing results, right? So looking at the concrete and just seeing the condition of the concrete, I was not surprised there. I was not super surprised. It's not a super corrosive environment either, not a highly corrosive environment. So, I mean, I think I was surprised to see like wood markings on the concrete. I was pretty shocked actually. And the wood markings photos that I showed, that's like all over the bridge, okay? It's not just like one area. It's not as prominent on the outside, but inside, underneath where it's been covered for 90 years, I mean, it's beautiful concrete.
This is a bit of a technical question about the analysis that you did and how you made the decisions. The only reason I'm asking this question is I worked on a spandrel arch bridge earlier in my career that had cracking in the short columns of the spandrel. Now, I'm going to tell you that this bridge did not have articulated hinges, right? And it also didn't have any ties or shear reinforcement, in the girders. Mm-hmm. And what happened was that it had relieved itself over time, and it was functioning, not as originally designed, but it's functioning. We addressed that. I'm not going to get into that, but I noticed you had tons of tie reinforcement, and I don't even know if it had an original spandrel arch, but was that a problem on this bridge? And obviously when you went through and did the analysis, you had to take that into consideration.
The column design was something that we had to evaluate. It was an issue. We had to dowel in some longitudinal reinforcement, but in terms of the shear, I don't remember it being a huge issue, but certainly it was something we had to evaluate. And yes, it was a challenge, and we had to do some iterations. But again, looking at the whole system, we were able to make it work.
So basically, you didn't have to change the reinforcement. The reinforcement was adequate enough not to cause cracking in the columns.
That's correct. Yep.
John, thanks very much for the presentation. Just real quick, you said you used design build as the method, or North Carolina chose to use that. How far along were your design plans that you ended up giving to the contractor?
Yeah, they were complete PE seal design plans that the contractor used to construct the bridge.
So did NCDOT see any savings from the design build methodology of delivering the project?
No, I don't think so. I mean, it was more, again, to basically make the contractors put forth a proposal so that they could be evaluated on their capability of performing the job, as opposed to competing on the price. Or nobody came up with a new design or a new concept that was not proposed by any of the contractors. Siva's got a question.
I just had a comment. Yeah, somebody was asking about the carbonation. We actually checked the carbonation. It wasn't too deep, and also we calculated the future carbonation effects, and it would last more than 75 years that, North Carolina was looking for.
Yeah.
Thanks, John.
Thank you, Tim.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.